Welcome to the Explainer. So, if you're someone who understands how traditional databases work, the centralized, editable kind, you've probably wondered how a blockchain is really all that different under the hood. What if you could build a database that nobody controls and where nothing, once it's written, could ever be changed? Well, that's the big idea behind blockchain. So, let's really get into how it pulls that off. Here's what we're going to cover. First, we'll see how blockchain stacks up against a database you're already used to. Then, we'll build a chain, block by block. After that, we'll peek inside a block's header, tackle the mining puzzle, and finally, we'll understand why this whole crazy process is what makes the system so secure. All right, so to really get it, we have to start with a direct comparison. How is a blockchain fundamentally different from the databases that pretty much run our digital lives today? It really boils down to two huge things. Who's in charge, and can you change the past? In your standard database, there's a central admin. They hold the keys to the kingdom, they can change or delete whatever they want. A blockchain just flips that entire idea on its head. The ledger is distributed, which means everybody has a copy. And, this is the critical part, new entries get added only when the group agrees. And once they're in, they are immutable, permanent. You cannot change them. Okay, so a distributed, unchangeable ledger. That makes sense. But what makes it a chain? How are all these individual blocks of data actually connected to each other in a way that's secure? The process is actually pretty elegant, but wow, is it powerful. So a new block of transactions gets created. Then, a unique digital fingerprint for that entire block, that's a cryptographic hash, is generated. The next block that comes along grabs that hash and puts it right inside its own header. And boom, you have a secure link. Each block is now pointing directly to the one that came right before it. Think of this hash as like a super secure digital wax seal. If you change even one tiny little bit of data in the previous block, a single comma, one number, anything, the hash for that block changes completely. It's something called the avalanche effect, and that would instantly break the chain, making it blindingly obvious to the entire network that something's been messed with. So each block points to the last one using that hash. Got it. But, a simple pointer isn't going to be enough. What other mission-critical data is packed into a block's header to make this whole system actually work and stay secure? This header, it's like the block's DNA. It has everything the network needs to check that the block is legit. And you see the obvious stuff, right? Like a timestamp, and of course, that super important hash of the previous block. But take a look at those last two items, the nonce and the difficulty target. These two, they're the secret sauce. They are the key to the entire security model. And here we can see what each part does. That merkle root, for example, is a really clever way to create a single fingerprint that summarizes all the individual transactions inside the block. But the real magic, the part that actually secures the chain, comes from those last two, the nonce and the difficulty target. Together, they create a really, really hard puzzle that someone has to solve. And that puzzle brings us to this huge challenge. If there's no administrator, how in the world does this global network agree on which block gets to be added next? Well, that is where mining comes into the picture. So this is where miners come in. You can just picture them competing in this massive global race to be the one who gets to add the next block. To win, they have to solve that puzzle we mentioned, and the only tool they have to do it is the nonce, a totally random number that they can change over and over and over again. So they start guessing at unbelievable speeds. Okay, so imagine this is the first try. A miner takes all the block header data, they tack on a nonce of 1, and they hash the whole thing. The result starts with 8A3C, which is way too high. It doesn't need the difficulty target, so nope, try again. All right, let's just fast forward through billions of guesses. They try another nonce, the new hash starts with 1E9F, still not low enough, still doesn't meet the target. And you gotta remember, every single one of these guesses costs real-world computing power and real-world electricity. And then, finally, after maybe trillions of attempts, some miner somewhere in the world finds a nonce that, when you combine it with the rest of the block data, produces a hash that starts with the required number of zeros. It meets the target. They've done it. They solved the puzzle, they won the race, and they've now earned the right to add their block to the chain. But why? Why go through all this incredibly difficult, energy-guzzling puzzle? What does all of this work actually prove? And why is it so ridiculously important? So here's the crucial point. The puzzle itself isn't the goal, it's the proof. This is what we call proof of work. By finding that winning nonce, a miner is proving to the entire world that they spent real time and real energy to solve it.
It's incredibly hard to do, but once it's done, it is super easy for everyone else on the network to check it. They just run the hash one time, and yep, it works. And this right here just brilliantly explains the whole security model. Look, to change a transaction in the past, an attacker couldn't just solve one puzzle. Oh no. They would have to re-solve the puzzle for that block and for every single block that came after it, all while trying to outrace the combined power of the entire global network. It's a computational arms race they are basically guaranteed to lose. It's practically impossible.
And this leaves us with a final, really big thought. This immutability that proof of work gives us means there are no do-overs. There's no central bank to call to reverse a mistaken transaction. So what does it really mean for trust, for risk, and for just plain responsibility when every valid action is final and permanent?
And that's our look at the core mechanics of a blockchain. If this helped you finally connect the dots between blocks and pointers and all that proof of work stuff, please do us a favor and like, share, and subscribe for more explainers.